NASA has formally identified the astronaut whose acute medical event precipitated the early termination of the SpaceX Crew 11 mission aboard the International Space Station. The decision to execute a full crew evacuation was not merely operational. The International Space Station resides in low Earth orbit. The station occupies a transitional boundary between Earth's dense lower atmosphere and the rarefied thermosphere. Every 90 minutes, the station traverses alternating hemispheres of Earth's magnetale. Astronaut physiology unfolds within this constantly shifting astrophysical context. Human biological systems evolved under 1G acceleration, geomagnetic shielding, and stable atmospheric pressure. In orbit, hydrostatic gradients collapse. Bone remodeling accelerates under reduced mechanical strain. Within this environment, even minor perturbations can cascade through interconnected physiological networks. The astronaut identified by NASA began exhibiting symptoms that, in microgravity, however, fluid compartments behave analogously to unconfined aquifers under reduced lithostatic pressure. Mission telemetry transmitted biometric streams in real time to terrestrial flight surgeons. Electrocardiogic rhythms were evaluated against expected microgravity-adapted baselines. Oxygen saturation variability was examined in the context of altered pulmonary perfusion patterns. Differential diagnoses incorporated cardiovascular dysrhythmia, neurovascular instability, inflammatory response, and radiation-induced oxidative stress pathways. The solar cycle phase at the time of the event was analyzed to exclude enhanced proton flux from coronal mass ejections intersecting Earth's magnetosphere. The ISS itself is a geophysical observatory as much as a laboratory. Its orbit intersects the South Atlantic anomaly, a region where Earth's inner Van Allen radiation belt dips closest to the surface due to geomagnetic field asymmetry. During these passages, increased charged particle flux penetrates spacecraft shielding, elevating radiation exposure for crew. Dosimeters continuously record cumulative ionizing exposure, measured in millisieverts. While levels remain within mission parameters, transient spikes can influence cellular oxidative stress and DNA repair pathways. The astronaut's condition crossed a threshold beyond which onboard countermeasures were deemed insufficient. The ISS medical kit, though sophisticated, lacks the comprehensive diagnostic imaging capacity of terrestrial hospitals. Ultrasound devices can evaluate soft tissue and vascular flow, but advanced neuroimaging or interventional cardiology procedures are impossible in orbit. NASA's risk management framework prioritizes preemptive evacuation when prognostic uncertainty intersects with limited treatment capacity. The Crew Dragon spacecraft docked to the station functioned as a lifeboat embedded within a broader astroengineering architecture developed by SpaceX. Autonomous guidance systems calculated phasing burns relative to Earth's geopotential field, compensating for atmospheric drag variations induced by thermospheric density fluctuations linked to solar ultraviolet flux. Undocking procedures synchronized with orbital mechanics to ensure deorbit burn vectors intersected safe re-entry corridors through Earth's atmosphere. Re-entry itself is a geophysical event. Kinetic energy conversion through atmospheric compression produces plasma sheaths around the spacecraft, reimposing hydrostatic gradients on cardiovascular systems that have adapted to weightlessness. The evacuation reduced station crew complement from 7 to 3, altering operational throughput across microgravity experiments in materials science, combustion physics, and exobiology. Research into protein crystallography, where diffusion dominates over convection, was temporarily deprioritized. Fluid dynamics experiments investigating capillary-driven flow in confined geometries were postponed. Even astrophysical instrumentation maintenance schedules were adjusted. NASA subsequently accelerated the launch of SpaceX Crew 12 to restore human capital in orbit. The Falcon 9 ascent trajectory threaded through stratified atmospheric layers, transitioning from tropospheric turbulence to near-vacuum exotmospheric conditions. Orbital insertion required precise delta-V calibration relative to Earth's gravitational, harmonics, and J2 oblateness perturbations. Within 34 hours, Crew Dragon achieved docking, re-establishing a 7-member expedition capable of resuming full scientific cadence. Yet the deeper significance of the Crew 11 medical event transcends operational logistics. It underscores the entanglement of human biology with cosmic physics. Solar variability modulates Earth's magnetosphere. Magnetospheric dynamics influence radiation exposure. Radiation influences cellular oxidative stress. Microgravity alters gene expression through mechanobiological pathways. Human health in orbit is therefore not merely biomedical. It is astrophysically mediated. Comparisons emerge with planetary exploration contexts. On the Moon, astronauts will confront reduced gravity at 1/6 g, regolith electrostatics influenced by solar wind charging, and elevated galactic cosmic radiation beyond Earth's magnetospheric shielding. On Mars, partial gravity at 0.38 grams and absence of a global magnetic field create a radically different radiative and biomechanical regime. Evacuation windows extend from hours to months. Autonomous medical capability becomes essential. The identification of the astronaut whose condition necessitated evacuation is therefore not an endpoint, but a data inflection. Post-flight analysis integrates omics sequencing, inflammatory biomarker assays, vascular imaging, and neurocognitive assessment. Investigators correlate physiological deviations with orbital radiation logs, geomagnetic activity indices, and mission workload metrics. Each dataset feeds predictive models refining astronaut selection criteria and in-flight monitoring thresholds. In planetary science, anomalies refine theory. Cometary outgassing revised models of volatile retention in the early solar nebula. Magnetohydrodynamic simulations reshaped understanding of solar flare propagation. Similarly, biomedical anomalies in orbit refine the theory of human adaptation to extraterrestrial environments. The ISS continues to orbit within Earth's magnetosphere, a metallic archipelago traversing plasma streams and micrometeoroid flux. Its existence is a convergence of astrophysics, geophysics, and human physiology. The Crew 11 evacuation demonstrated that even within a highly engineered system, the stochastic nature of biology persists. The astronaut at the center of this event becomes part of a lineage of data points stretching back to early Mercury, where limited telemetry constrained understanding of in-flight physiology. Today, continuous biometric streaming, radiation spectrometry, and orbital environmental monitoring create an unprecedented resolution of human cosmic interaction. As NASA prepares for Artemis lunar expeditions and eventual interplanetary trajectories, the lessons extracted from this medical event will inform habitat shielding design, artificial gravity research, telemedical AI systems, and countermeasure pharmacology. The boundary between astrophysics and medicine will blur further. In orbit, beneath auroral arcs energized by solar wind and above tectonic plates drifting across Earth's lithosphere, astronauts remain biological systems embedded in a cosmic framework. The Crew 11 evacuation was not failure. It was adaptive response within a complex astro-geophysical system. The International Space Station continues its geodetic path, inclination 51.6 degrees, within its pressurized modules, research resumes. Outside, plasma flows, meteoroids intersect, and solar photons stream outward from a fusion reactor 150 million kilometers away. Human exploration persists at the intersection of stellar physics and cellular biology. And every medical anomaly in orbit becomes another equation in the expanding calculus of living beyond Earth.